Effect of concentration and the temperature on electrode potential. We know that electrode potential will change by changing the concentration and the temperature of an electrode. If we have a particular metal, present in a solution containing its own ions, say for example we have a zinc rod here, and it is present in a zinc sulfate solution. Now, by changing the temperature of this, of this solution, the electrode potential of the zinc will change. Similarly, by changing the concentration of the zinc sulfate solution here, will change the electrode potential. The Nernst equation, actually, this equation, it tells us the quantitative effect. How this temperature and the concentration can change the electrode potential. So, according to this Nernst equation, the electrode potential of an electrode will be equal to this standard electrode potential, when we have the 1 molar concentration and the 25 degrees Celsius. That's what you call as the standard electrode potential. Standard electrode potential is the electrode potential of an electrode at 1 molar concentrations and 25 degrees Celsius. That is the standard electrode potential. Now, by changing the temperature and the concentration from these standard values, we will change, electrode potential will also change. So that means the electrode potential of an electrode will be equal to this standard electrode potential minus RT by NF. This is actually as per the Nernst equation, RT by NF ln metal concentration by the metal ion concentration. The metal Mn positive, let me write it like this, Mn positive. Now this is the Nernst equation. So here, this R is the gas constant. This is the gas constant. We know its value is 8.314 joules per Kelvin. The T is the temperature in Kelvin scale here. This is the temperature in the Kelvin scale. N is the number of electrons, that are lost or gained by a metal. So, for example, for the zinc, it will be N will be the 2, and if it is a silver ion, so the N will be 1. F is the Faraday's constant. This is the concentration of a metal, which is always taken as the 1. The molar concentration of a solid substance is always taken as 1. And this is the Mn positive, means the metal ion concentration, the molar concentration of the ions in the solution. How much is the concentration of the zinc sulfate, suppose here. So that means changing these concentrations will also change the electrode potential. And now we can also rearrange this equation. We can try to simplify this. It will be E naught minus, let's say this N in ln here. If I change it into log, so I can see it is 2.303, because converting the ln into log will be multiplied by the 2.303. RT by NF ln the metal concentration, as I said, is always taken as 1. So it will be 1 divided by the molar concentration of a metal is always taken as 1. The molar concentration of the N positive ions will be Mn positive here. And since we know that these are the constants, and F is the Faraday's constant, which is actually 96500. This is Faraday's constant. R is a constant, and temperature, if you take room temperature here, if the electrode potential, we take the temperature at 25 degrees Celsius. Now 2.303 RT by F, when you simplify this equation, when you simplify this part here, this one, 2.303 RT by F, so you can write down here, you can see this electrode potential will be equal to E naught, the standard electrode potential, minus 2.303 RT by F. When you simplify this value here, R is the constant, T is temperature, F is the Faraday's constant, it will be 0.0591 divided by the N, 1 by metal ion concentration, log of the 1 by metal ion concentration, Mn positive. Now this is the equation that we can use, okay, to find the electrode potential of an electrode under different conditions, not under the standard conditions. So let's take here an example. We have a copper electrode dipped in a solution of 0.1 molar copper sulfate at 25 degrees Celsius. and we have to find the electrode potential of this electrode at this concentration. The standard electrode potential of the copper is 0.34. So basically we have a copper electrode dipped in a solution of a 0.1 molar. This is not the 1 molar, this is 0.1 molar copper sulfate. So we have to find the the electrode potential of this copper at 0.1 molar concentration. So when you decrease the concentration from 1 molar to 0.1 molar, so we will see how this electrode potential will change. According to the Nernst equation, we know that the Nernst equation is this: electrode potential is equal to the standard electrode potential minus 2 or I can say it is 0.0591 divided by n log of the 1 by metal ion concentration. This is what we just learned. So over here we have the copper electrode. We know the copper sulfate ion, copper ions, they will take 2 electrons and they will form the solid copper. This is the electrode reaction. Now, which means that the N for the copper here is 2. The N for the copper here is 2. So that means I can put the values here. The electrode potential will be equal to standard electrode potential, which is 0.34. Under standard conditions it is 0.34 volts minus 0.0591 divided by 2 log of the 1 by metal ion concentration is 0.1. This is 0.1 molar, 1 by 0.1. Now 1 by 0.1 I think is 10, so log 10 into 0.0591 divided by 2. When you simplify this one, we will get actually the electrode potential will be 0.34 minus 0. This will be 0.2. So then the electrode potential will be 0.34 minus this one, so it will be 0.310. So which means that the electrode potential at a 0.1 molar concentration is 0.31. So the electrode potential decreases here by decreasing the concentration. By decreasing the concentration, the electrode potential also decreases, because at 1 molar, when we have a standard condition 1 molar, at 1 molar the electrode potential here is 0.34, but at 0.1 molar the electrode potential is only 0.31 volts. So that means decreasing the concentration of the metal ion will decrease the electrode potential.